Okay, so let's continue with OpenCV. So this topic is linear filtering, and as we all know, we already have discussed the different kind of filters. For example, Gaussian, mean, median, Sobel, all these type of filters. So in this again, we are going to discuss in brief detail about Gaussian and median filter. So we all know what Gaussian filter does is it smooths the image. I mean it blurs the image. For example, if you remember, this is something a Gaussian blur looks like. For example, if we talk about its matrix, see filter is a matrix. Now in this matrix, the mid values will be higher. For example, 0.56. Now as you go to the corners, the value decreases. For example, here the value will be 0.01. The here the value will be 0.10. Likewise, it will increase to the mid. Okay, so this is your Gaussian filter, if you can remember. Now this is the code if you want to implement Gaussian blur on an image. So again, the library, Python imaging library, input image, and then in this variable we are applying this image filter, and then we are just saving this image filter. So the code is very straightforward, but you can see the radius over here. So in the theory we discussed about the sigma. Sigma means the variation from the corner to mid, right? So again, this can be said as radius in here in image filter library. Okay? So radius, for example, if we are writing radius as 5, the image will be less blur, and if we are writing radius is equal to 10, the blur will be more. Okay, so there is an example that I applied on the same image. So in this image, using this code, in one of the in first attempt, I updated radius as 5, and in the second attempt I updated radius as 10. So you can see the difference in these two outputs. This is your input, and on providing sigma as 5, the output will be something like this. And if we are writing radius as 10, the blur will be something like this. Okay, so this was your Gaussian filtering. Now next in the linear filter is median. See, there are many linear filters, non-linear filters, but for the sake of implement, I'm just giving you example of two. When you have to study for exams, you should be considering all of them. Okay, so we're just discussing these two, and you can change a few lines, and then you can implement all of these. So again, median filter that we have already discussed, this is your input and this is your output. So in median filter, what we have already discussed is if there would be some noise in this image, that would have been rectified here. Okay, but since this image doesn't have any noise, so this is your output. And next topic is histogram equalization. Now I want all your attention here, because this is a very different kind of topic, not a very difficult but a different topic. Okay, so let us start from here. So you can see this, if you can see this histogram, let me zoom it a bit. Yes. Okay, so you can see this one. So you can see the intensity, the low intensity pixels are more. For example, you know that 255 means brighter and 0 means darker. So you can see in this image is more likely to be a darker image. Okay, so there is no gray values, there are no white values. Okay, so you can see this is the image that we are talking about. There are more black pixels, while on the other hand, if you talk about an image that have more white pixels, this would be that image. Okay, so you can see the histogram over here. There are no dark pixels, there are only few gray pixels. Okay, now there is another variation, which is all the intensities, all the pixels are in the mid. So this will be a very dull kind of image. As you can see, everything is gray, no white, no dark. Okay, Now fourth one is pixel of all intensities. So this should be a perfect image, right? There is a very bright pixels, there are dark pixels, there are gray pixels, right? So the histogram is scattered. Okay, so this should be the perfect image. But see, if we got something like this, and if we want to achieve something like this, so that process is called histogram equalization. What we do is there will be this histogram and we'll scatter it a bit. Okay, we'll try to scatter it. Now let's see how we do this. So for example, this is an image, original image, and you can see this is a bit darker, and hence you can see the pixel values are around 0 to 100. And this is histogram equalized image, which is, you can see the pixel values are scattered, right? So so as I said, I want all your attention over here. Now let's suppose this is an image. Okay, now you can see in computer science, if we want to store a value, we count it in bits. For example, if we want to store a value 3, okay, so see, it is in, we compute this in square values. For example, 2 to the power 2 is 4. Okay, 2 to the power 2 is 4. Now if we want to store one value, see, 1 means numeric 1. If you want to store 0 or 1, if you want to store either 0 or 1, we only need 1 bit. Are you getting it? हमारे पास सिर्फ एक ही बिट है, हम उसको 0 कर सकते हैं, उसको 1 कर सकते हैं. Okay, so in that's how we can store only one number. Okay, but what if we want to store 2? If we want to store 2, we need 2 bits. Okay, 2 bits. For example, now 2 bits means 2 to the power 4. 2 to the power 2. That means 4 numbers are allowed. 4 number कौन से? 0, 1, 2 and 3. So now if we are taking 2 bits, that will allow 4 numbers, है ना? And every time we are talking about this, we should start from 0. Okay, so now from 0 to 3, there will be 4 numbers. So now, but if we want to store values using 3 bits, so 2 to the power 3 is 8. So using 3 bits, we can go up to 8 numbers, up to 8 values. Okay, now likewise, if you want to store number 10, so for example, if you're talking about this 8, so 8 means 0 to 7. Okay, so right from the 0, the values are starting, and up to 7 we can insert the values. But if we want to insert, let's suppose 10, if we want to store 10, we cannot go on like with 3 bits. For that, we have to expand it to the 4 bits. We at least need 4 bits. So now, since it is now 4 bits, so 2 to the power 4 will be 16. Now it will store 0 to 15. Is this clear? Now see, if it is not clear to you, you can just rewind the video back. So the main funda is, in computer science, we need bits to store data, right? So if you want to store a number 0 or a number 1, you can use only 1 bit and you can do that job. But what if you want to store number 2? So in order to store 2, you cannot use a single bit. You at least need 2 bits. Okay, so, and if you want to for 2 bits, that means 2 to the power 4, you can 2 to the power 2, you can store up to 4 numbers. Okay, now if you are using 3 bits, then you can store up to 8 numbers. Okay, now whenever we are talking about these numbers 4 and 8, one should remember that the ranges are from 0 to 3. Okay, 0 to 3. And if we are talking about 8, then the range will be 0 to 7. Okay, Now it should be clear to you, and if it is not clear to you, you can again rewind the video back, or you can also text me. We can set a Google Meet. Okay, so one thing should be clear now. If you want to store, if you have only one bit to store data, you can either store 0 or 1. But if you have 2 bits, you can also store 2 and 3. Now if you have 3 bits, you can store 4, 5, 6, 7. So is this clear? I hope this should be clear to you. This is not an interactive lesson. So okay, now one thing, I have a question. For example, you can see this image. What is the maximum number that you can see? Maximum number is 5, right? So if we want to store everything, the maximum number is 5. So how many bits do we require? Can we use it via only 2 bits or 1 bit? I don't think so. So here up to 7 we need 3 bits, right? 3 bits means 0 to 7. So if that's 5 is here, 5 can only be used when we use at least 3 bits. If you're using 4 bits, that we can also do that, but we want minimum number of bits. Okay, so let's suppose this falls in this category. Okay, 3 bits. Now what we are going to do is, see, why am I explaining this is, for example, in the exam you might see 10 written over here. So if you can see 10 here, that means that falls in this category, right? So likewise, and now since we know that the range is 0 to 7, we have written these range over here. Okay, you can see gray level 0 to 7, simple, not very complex. Okay, so 0 to 7 simply हमने यहाँ लिख दिया. Now next is the frequency of these pixels. For example, you can see 0, 1, 2, 3, 4. How many times you can see 0 in this matrix? It is 0 times. How many times you can see 1? 1 is 0 times. Now if I ask you how many times you can see 5, so if you count 5, 1, 2, 3, 4, 5. So there are 5 values. So corresponding to 5 we have written 5. So likewise, when we count 4, there are 14 number of 4 values. Okay, so this is your distribution. Now if we plot this distribution, it will look something like this. Okay, so this is your input pixel intensity histogram. So this is your very much like this input, right? This is very much like this input. Okay, so now the input must be clear to you. If it is not clear to you, you can pause. You can start the lecture. You can start over the lecture again. And if still you have any doubt, you can call me, text me, or whatever you want. I will be clearing your doubts. Okay. Now, so let's recap. First of all, you can see all these values. Now you can see maximum is 5. So maximum falls in this range. Okay. Now what we have done is 0 to 7. We simply write 0 to 7 over here. Now, how many frequencies? For example, 5 is written 5 times. So we have simply written 5 over here. 3 is written 6 times. So we written 6 over here. 4 is written 14 times. So 14 should be here. Now, once this table is clear to you, we can easily plot the histogram. Okay, so this is the histogram. 0, 1, 2, there is nothing to show. So that's why there are only 3 values. And this looks very dull image, if you can see like this. This is a very dull image. Everything is at mid. Okay, now next step is, this is a a step that needs your attention. But this is a very easy step at the same time. Okay, so next step is, again, that we can see 0 to 7. We simply write 0 to 7 over here. Okay, clear? Now, next step is to simply write the corresponding values. For example, on the 0 we have 0. For 3 we have 6. For 4 we have 14. Okay, So for 4 we have 14, for 3 we have 6. So again that table, we only copied that table here. Okay, so now this table is here. Now in the bottom what we are doing is we are adding all the values. Okay, 6 plus 14 plus 5, that means 25. Clear? First two columns clear. Now these two columns should be clear to you. Now next thing is the sum is 25. Now we are dividing each one of these with sum. We are dividing each one of these with the sum. So for example, 0 divided by 25 is 0. All these are 0, and 6 divided by 25 is 0.24. Okay, likewise we will divide this. Okay, now the column 3 should be clear to you, and if it is not clear to you, just rewind it. So what we are doing is simply these two values are, we are copying from this table, and then we are just counting the sum of this. Next, in the next column we are dividing everything with the maximum, with the sum. Okay, 0 by 25, 14 by 25. Now up to 3 columns things should be clear to you. Now in the next column we are just counting running sum, nothing complex. For example, 0, and now 0 plus 0 is 0. Okay, 0 plus 0 is 0. Now 0 plus 0.24 is 0.24. Okay, are you getting it? Simply we are summing n minus 1th value. Okay, now here you can see 0.24. So what we're going to do is we'll take the next value, that is 0.56. We'll simply add 0.24 with 0.56 and the output will be 0.8, as simple as that. Now again 0.8, we are adding 0.2 to it. Now it will become 1. Okay, same, we'll adding 0, we'll add 0. Now finally these will be your values, running sums, or you can say cumulative values. Okay, now up to 4th value, 4th column, things should be clear to you. Now if I ask you the gray values, what is the maximum values in this column? What is the maximum value in this column from 0 to 7? Absolutely 7, right? So what we are doing is we are multiplying maximum with these values. Okay, 0 into 7 is 0, 0 into 7 is 0. So up to 3 the result will be 0. Now 0.24 multiplied by 7 is 1.68. Likewise 0.8 into 7 is 5.6. So we are just multiplying these values with maximum gray value. Okay, now up to column 5 things should be clear to you. Now if you are able to understood this, now this is just a round off. Okay, we are rounding off to seal value. For example, for 1.68 it will become 2, for 5.6 it will become 6. Okay, rounding off, as simple as that. So what we have done, first of all, we just copied these two values, counted the sum of these values. Now the sum will be divided with these values. Okay, for example, 6 divided by 25 is 0.24. Now since this column is clear to you, now we are just calculating running sum. For example, 0 plus 0 is 0, and 0.24 plus 0.56 is 8. So likewise we are just calculating this. Now once this is calculated, we are taking the maximum gray value and we are just multiplying this. For example, 1 into 7 is 7, 0.8 into 7 is 5.6. Okay, now on getting this output, we are just taking the round off. For example, 1.68, 2, 5.6, 6. As simple as that. Now since now things should be clear to you. Now you can see this is the output. Okay, histogram equalized output. Now you must remember this image. Now what you have to do is, wherever there is 4, you just have to replace with 6. Wherever there is 6, you have to replace with 7. 7 should be replaced with 7. Okay, is this clear to you? All the previous values, for example 5, should be replaced with 7. And if you can see in the older matrix, if there is 4, that should be replaced with 6. Okay, as simple as that. Now this is your previous image. Now instead of 4, we are writing 6. So again, we are just replacing the values. So this will be your output image after equalization. Okay, done. Now again what we are doing is we are counting the frequencies. For example, 2 has appeared 6 times, so we have just written 6 over here. Okay, so this was your previous input image and this is your output image. So now we are just plotting the histogram of these two images. So this is your input image and this is your output image. So this is your pixel, so this is your histogram equalization. So you can see that the output is not very good, but it is somewhat better than the previous state. At least it is scattered a bit. Okay, so this image might not be a very great example of it, but it has given a very good examples, very good outputs. So you can see the code is here, and if we apply the if we apply the histogram equalization on the image, on the image that we have used here, the output will be something like this. So first of all, you need to convert it to the grayscale, and then this will be your output. Okay, so this was your histogram equalization. If you are unable to understand this, I'll recommend you to go back and start it from the beginning. And if you have any doubt, you can ask me anytime. Next is Gaussian convolution. We are not going to discuss this, since Gaussian convolution we have already discussed numerous of times. Convolution, you all know what convolution is. Gaussian, you all know what Gaussian is. Even we have discussed just discussed it. Now next is separable Gaussian convolution. Separable Gaussian convolution. Okay, so now you can read it, but I'll explain you in a very simple manner. So what a filter does is it will slide through the image. For example, filter can be of 3 by 3, 5 by 5 by 5, 7 by 7, 21 by 21. Okay, so all these are different kind of kernels. For example, this is your kernel. Now in the next iteration, what it will do is it will slide, and this will be considered. And in the third iteration, it will again slide, and this will be your consideration. Okay, so likewise in the fourth iteration, it will consider this. Okay, likewise, so this is a very small image. You can see this is a 5 by 5 image. Now what if you have a 3000 by 3000 image? What you're gonna do in that? So one thing is clear, all these are computation, right? So what it is doing is it is doing computation. Now if you are considering a 3 by 3 kernel, and if the image is of 3000 pixels on one side, so you can assume how computationally exhaustive that will be. Okay, so there is an approach that is called separable Gaussian. But what it says is, for example, if you are considering this 3 by 3 matrix, this 3 by 3 kernel, so you can see that is there a possibility that your convolution can be separable into 2 vectors. For example, this is your X filter, this is your X vector, and this is your Y vector. So one thing is clear. See, there are, what if we multiply 1 by 3 matrix with 3 by 1 matrix? What will be the output? That will definitely be 3 by 3. Okay, so that's our approach here. If we can divide our matrix, our convolution, our kernel into two such vectors of x and y that can later be combined like this, that now if we can do something like this, that will be less computationally exhaustive, and it will save a lot of time, money, and everything. So this will be very less expensive operation. So whenever we say that this is a computationally expensive operation, that means, for example, when we are running an image processing, for example, you are hired for a Microsoft to do certain tasks. Now they have everything. For example, they have bandwidth, internet bandwidth, they have storage. Okay, might be 256 or maybe 1 TB. They have different RAMs. Okay, so all these are resources that comes with a cost. Okay, let's suppose you are consuming resources of 100 rupees per hour. Okay, now again you are employed and your package is 12 LPA. Okay, that means 1 lakh per month. Now, for example, if you are if you are waiting your task to be done, for example, if you are waiting for your output in, for example, for 2 hours, so that will cost a lot to company, right? So that's why it will be computationally expensive from the point of view of an organization. Okay, so now the computation includes many costs. For example, time, right, and the resources you are using. So everything sums up the cost of computation. So if we can use a kernel that can be separable in these two vectors, that will save a lot of cost, time, and resources. So that will be a huge saving. Next is Gaussian derivatives. So what Gaussian derivative does is, basically you can read everything. So basically derivative you all know. First, let's see this. You know this, maximum value, minimum value. And we already have discussed the derivatives. First derivative, second derivative. So what we've done here is, this is the x derivative. So you can see this is positive and this is negative. Okay, so derivative यही करता है हमारा, एक पॉजिटिव को चेंज बताता है बेसिकली, राइट. नाउ जो गॉसियन डेरिवेटिव्स है, इट हैज इट्स ओन advantages. For example, edge detection, and for example, the derivatives we have already discussed the derivatives in gradient based edge detection, right? And we also have discussed the double derivatives in Laplacian. Okay, so like derivatives are very useful in edge detection and in feature extraction, in noise reduction. You can read out all this. Now I have applied this code. So if you want to, this code is not very, you can just simply copy paste this code if you want to. Now this is Gaussian derivative that I run. This is my input image and this is my output image. So you can easily see that the edges are clearly visible, right? The edges are clearly visible over here. So that's why Gaussian derivatives are used. Now next is our Canny edge detector, and I already told you in the class that we are discussing the Canny edge detector in the second unit, and we are not going to discuss this in our fourth unit. So again, you can see this input image of tomato leaf affected with late blight, and the code, and this is the code we have used for Canny edge detector. See, this is a very simple, straightforward code. We have converted this to grayscale and just simply applied a library function, and the output is, you can see the output is here, the last one. This is the output of Canny edge detector.